we have seen more application, right, that requires, right, neural network. And neural network, generally speaking, right, they are very power intensive in terms of they would need lots of data pipeline to train the neural network model forward, backward propagation to achieve the not just time to result, but in terms of achieve the accuracy of this model, so we can deploy and infuse that a model in business use case. And what we have seen is like depends on the type of model algorithm that you're using, right? For a classical machine learning algorithm, CPU is a very good fit, generally speaking, right? Don't get me wrong. In terms of times, boosting algorithm, etc. But when we come to the neural network, right, use case, which I'll cover in the next slide, we have seen CPU itself, right? It may not satisfy the power hunger requirement of neural network, and here's where GPU comes in place and to the rescue. And I think we have worked with multiple different clients across industry, and this is we now seeing that the time era of deep learning, neural network application arrives, right? And you can see different wide range of use case, right? Including commercial banks, right? We work together to improve fraud detection with this like mass detection for unattended ATM, right? Using image object detection. And in healthcare, research hospital rely on deep learning to as radiologists with diagnosis, with to help improve patient outcome. And one of the client retailers, right? They use deep learning to help forecasting inventory, use LSTM model for better efficiency and customer satisfaction. So we are just scratching the surface here, and there'll be more and more success story around deep learning out there that we still yet explore and work with our client. Now, this is why we are here. I want to share this AI journey story with you. We see a common same challenge. It's like a pattern. Same challenge when we talk to our clients. All of this client that we work with, such as like IT leaders, ML ops, data science team, right? They find themselves with kind of like limited ability, right, to allocate and control expensive GPU compute resource, right? So you can think of when they get started, they have 1 or 2 data scientists. That's easy. They procure a GPU box, and then this GPU box will sit under this individual desk. So they get, this data scientist will get full control of the GPUs, right, and on and off, right, when they launch a job. But think about the same time, right? There's lots of idling time. If the data scientist is not using this GPU, they will sit under the desk, right? And with this limit ability, right, to manage allocate GPUs, right, across multiple data scientists, a lot of business. Right now, we see they find themselves into a situation they're forced to create kind of like own infrastructure in silos. So each department's or data science team or lab business, they create their own GPU grid and share across only within their own departments. Now, this type of development pattern is costly and inefficient, right? And this is where when they come to us, right, and they said, we have this problem now. We have very low utilization of GPU resource, and GPU is so expensive. Just speaking, like we talk about 5 figures per GPU card, right? So how can we make it more efficient, right? And at the same time, how can we make sure that there's nobody or data scientists will be starving for this GPU resource and will be non-productive? So this is a classic scenario, right? You can see there are 2 data scientists, right? How they actually, the real life, they're fighting for GPU resource. So we have Mary and Bob, and you can see here, right? Bob comes in, launched the notebook, right? And GPU notebook, start to build a model. Then he can ask number of GPUs in the grid and hoarding all GPUs. And then when the second data scientist come in, Mary, right? We try to submit his job, her job, and try to get the GPU to run. She's blocked essentially, right? Until Bob jobs finish, and then this GPU will become available from the resource pool, and the memory can take advantage of it. So you can see this fluctuation in terms of GPU utilization, and this is one aspect of it, right? But the second aspect is really you will have data scientists, right, become non-productive. And keep that in mind. What we want to achieve here is both to drive the productivity on two aspects. One is the hardware investment. The second is the data scientist time, right? Because they're also expensive, right? They are the key to help to explore the state of art, right? To build models, right? To help address, which helps addressing business challenge of their own company or with respect of their client. So significant investment, right? As I mentioned, right? 50 grand, five digit, right? For procuring a GPU card. You don't want this GPU card sitting in idle time and not delivering, and which drive the total cost of ownership, right? And this is exactly Watson Machine Learning Accelerator we introduced as Cluster for Data. We are the leading vendor in the market, right, to tackle this exact same challenge, right? How do you efficiently share GPUs across team of data scientists and drive up utilization and lower down the total cost ownership? And in typical scenarios, right, we work with the client, we observe they could get about over 30% boost in terms of GPU productivity, right? This is a huge boost in terms of return of investment, ROI. If you consider this high price of GPU today, and more importantly, we make this technology simple and easy to use, right? Which is often a reason why client chooses over competitor. And I will show you how it works right now. Okay, so before we jump into live demo, so
hey Kelvin, actually before we do that, there's a question that came in. I want to get you on the question quick. The question came in. Sure. The question asked, does WMLA support MIG, which is a multi-instance GPU on NVIDIA GPU cards?
In this question is in 4.0, right? We will support NVIDIA A100 GPU card, which will also support the MIG capability.
Perfect.
Okay.
Thank you.
No problem. Good question. So before I jump into the live action, right? Show and tell live action. Quoting back from the use case Travis talked about, data scientists managing the data science workflow in Watson Studio, and how do you actually drive that execution and offloading, for example, this aggregate data hungry require lots of powers, right? Running in executing that job in Watson Machine Learning Accelerator. Now, what we position is we offer choice for our end user, right? So depending on, I would say, the familiarity of the programming language, and you can see this table here. There's choices, right? So let me get started. So on the left-hand side, in Watson Studio, right, client can programmatically, right, using the Watson Machine Learning API or the wrapper Python client, right, to submit and offload the GPU model training, neural network model training running on Watson Machine Learning Accelerator, right? So that's one way. And at the bottom left corner, we also introduced this experiment UI, a few step click tool, and you will see that in a bit, to drive that workload in Watson Machine Learning Accelerator. Now on the right hand side, we have we also provide Watson Machine Learning Accelerator REST API direct, right? So equivalent same functionality, what you could also leverage on the left-hand side, on the right-hand side. So it depends, right? Where you get starting point, and the data scientist, what's the preference of programming language API they will leverage? You can do either both of the way, right? And on the right-hand side, you can see like the Watson Machine Learning Accelerator REST API. You can run it either from your laptop, right? So like, for example, when I build my samples, you will see in a bit, sometimes I actually just log onto my MacBook and then launch a notebook, and this is how I build my develop my sample. All right. So two demos, right? So I will start with talk about the AI journey, right? So we'll start with think about a single data scientist, right? How you could leverage Watson Machine Learning Accelerator deep learning service to achieve time to result, deliver faster result across these two demos. First is leveraging our auto hyperparameter search to search the optimal set of the model associated with their neural network architecture data set, right? To find that optimum space of the parameters to kick off the training. And then we'll see in the next demo, we apply that optimum set of parameters. And we can see that the performance in terms of training the neural network model with CPU, and then how we can accelerate that training, expedite that training time using using the accelerate deep learning surface, train that model in GPU in Watson Machine Learning Accelerator. So a bit of an introduction of hyperparameter tuning. So this is actually one of the in the AI lifecycle that data scientists spend lots of time, because to be able to search this different parameters to kind of like to tell the model how to train, how to learn, right, from the data set, from the data pipeline that we're feeding into the model. It depends. The more complex of your neural network, the more parameters you need to tune. So without the data scientists general, they take that brute force approach. They try different combination of parameters and try to hopefully they can find the best match, right? Of course, they define their training metric to observe that search, right, an experiment. What we offer here is auto hyperparameter tuning, the capability. You can think of when able data scientists, right, to define the search range of all of the parameters. At the same time, select their favorite set of algorithm, and out of box we support random tree TPE, Bayesian hyperband, state-of-art algorithm. And at the same time, right, one of a client, they have an advanced data scientist team. They come back to us, they asking, hey, we're building our own algorithm, right, for risk analysis model. Can I apply my own algorithm to do the search? And that's why we enable this new feature recently, and enable this client to bring in their own algorithm, right? And we'll take advantage of our scheduling capability to be able to run multiple experiments across the grid. So you can think of you have like this client, they have 64 GPUs. So overnight, they will submit a batch job using the REST API, and they could automate, right, for 8 hours, right, when there's no activities like daytime, right, with data science coming in the office. They take advantage of this capability to search and find out 64 experiments run at the same time across 64 GPUs. Each experiment running and occupies 1 GPUs. And then running over that for 8 hours, and then come back later on in the morning, they will see the result. Let's see how it works. So I'm bringing up my copy for data environment. So Travis, can you see my my screen, my web browser?
Yes, we can see it.
Perfect. So I'll skip this. So for this demo, we're going to use Watson Machine Learning Accelerator REST API and how data scientists doing experiment to search for the optimum set of parameters. So I'll skip this one as I just go through that in the previous slide. So the first thing we're going to do, right? So this, by the way, this is the Cloudpath for Data 3.5.0 version, and this is a Watson Studio Jupyter Notebook. And right here, I'm showing you like how we can leverage using Watson Studio as a control plane, and then submit my experiment, right? Request and training running in Watson Machine Learning Accelerator. So first, we will load a bunch of data science libraries, right? Like pandas, right, etc. So first, then we'll construct the REST API endpoint. So this is where we tell, right, please submit this job to the REST API endpoint of Watson Machine Learning Accelerator, right? So now we'll lock on, generate a token. We will use it later on to access the deep learning service by the REST API. So the first one we're going to check right? So this is the first REST API. And I print over here, so everyone can take a look where it is. We want to, our data scientists that come on board, I want to see if there's any experiment running. So right here, there's none, because I'm the sole user of the system. Now, next, right? So what we're showing here is in this sample, we are taking a PyTorch means model from open source. And the next few slides, just want to show like lots of code change. For example, we call that data science will provide the range of parameters. How can we actually load the selection of parameters and inject it into the model and then execute the experiment? This is the code change exactly how we load, right? So this is minimum code change, I would say, right? So this is showing for this demo, right? We're trying to search learning rate, right? Using the random algorithm, and we divide the search range, and this is how we pull, right, the learning rate, right? That is selected by the HPO engine, and then we inject that into the model, and then run the search. And at the end, of course, the metric, right? So user can define the metric, right? And how we collect that metric later on, that will consumed by the HPO engine, and then pick up the best experiment with the best outcome. So right here, this is the actual code. Well, I'll skip that, but I just want to show you the code, right? What it is, and I'm using the write file extension to output this cell, the actual Python code, into file in Watson Studio working directory. Okay, so just a bit of quick touch, right? So here's what I talk about, in terms of loading the learning rate, right? Those select by the HPO engine, and then kick off the experiment. Okay, and next, right? So here you can think of how data scientists select in this JSON object, select their favorite set of algorithm, right? So as I said, right, we support the 4 algorithm out of the box, and you can also put down your own algorithm, plug in your own algorithm to do the search, and then the control plane. In terms of like the 2 dimension, one is the maximum running time, right, of this experiment, and then the maximum number of experiment you want to run. Now the next, this is another key attribute. Now this is define how many experiment you want to run in parallel. Now for my environment, I only have 2 GPUs. So right here, I'll put down 2, right? So, and then you'll see in a bit, 2 experiment will kick off and run in parallel. And they define the metric, right? So how you want to measure experiment, right? We support minimize or maximize strategy. So it depends, right? Any parameters, right, that you want to measure, you leverage to measure your experiment outcome. You can leverage that over here. And then next, right? So for this demo, I only put down learning rate, but you can put down as many as parameters you want to search in this block, right? So you see here, I put range and from 0.01 to 0.12. So I tell the HPO engine, please start searching, right, using this random algorithm, and search across this range for this learning rate. So let's run this, and then we'll kick it off. So the last part, we consider the REST API, passing on to the actual Python code model, and my JSON object that includes all of the my search space, etc., and send over to Watson Machine Learning Accelerator. And now we use a REST API. We can use the same different REST API again, and we can query the status of this model search, and it will pull like the search for every 5 seconds. So for time for the demo, right? So I'm gonna switch over. So this is a complete run. I just ran that a couple of days ago. You see here, and imagine there's only 2 experiments. Coding back like my client, right, running 8 hours overnight. They run thousands of experiments. So it would be painful, right, if you need to navigate each experiment, try to look at the result and see what's the best. But instead, in the recipe, when you call it, right, when all this experiment finish, what we're going to do is we're going to put the best one, right? We'll still print out every single experiment with the corresponding metric, the parameters that we're trying. But by the end, we will pull the best one out of everything, out of all the experiment, and display over here. So it becomes handy, right? When you have 1,000 experiment, you can pick that value, right? Just parameters, and then move on to train your model. So that's what I'm going to do next. I'll show you. Okay, actually, this is finished, right? So this is just what I run, and it's finished with very quick because I only went for one epoch for this demonstration purpose. So next, let's take that parameters, right? And we will show you how to apply that and run the same model and compare the performance across CPU and GPU. So I'm going to load my next model. Next notebook. So to get started, we will do two execution here. One is we will train exactly the same model using the CPU and train that in Watson Studio Jupyter kernel. And then we'll send this job over, right, to train this model with Watson Machine Learning Accelerator deep learning service with GPU, right? So we're using Touch Vision. So over here, again, we're defining a bunch of helper class. We'll show you in a bit later on using the REST API, right? And again, we construct, I'll go through very quickly on this one. We'll just do the same construction of the REST API server, locking get a token. Now first, so again, this is PyTorch REST model. We download straight from open source. From GitHub, this is PyTorch RESTnet. Now, I want to keep in mind, the first one of code change I made is to tell the model, I want to train that model without CUDA, which means I want to train that model with CPU, without GPU, right? So we set the false here. And now, same approach, right? This is the model, it's a direct copy and paste, right? So we output that to Watson Studio working directory. And next, we're going to train that model with one epoch, right? So I'm not going to run this the train here, execute the model here, and you see in my experiment, in my execution, I bump up the kernel runtime to 16 vCPU with 32 gig memory, and it takes approximately still with 26 minutes to complete one epoch training. And I'll show you right to the end what's the actual training this reflecting that training time, right? Slightly off, but you get the idea, right? So 30 minutes, right, to train one epoch of PyTorch RESTnet neural network. And next, we're gonna make one line of code change, right? And then we'll pass that model, offload that training to Watson Machine Learning Accelerator. So we'll do the same thing before I output this model. What I'm gonna show you, right? So I make one slight code change, right? This time I enable CUDA, right, and set to true. That means like I want to train this model with GPU. Again, so right here we construct the REST API, and we're going to submit the job. So over here, right now we send this job over to Watson Machine Learning Accelerator, and we'll start kicking off. And every 5 seconds, we use a different API, REST API, and query the status of this training. This training will run around for 140 seconds. So again, I have the complete run, which is last night actually, essentially, a couple of days ago, sorry. And you see it's 134 seconds. And you see it drives like more than like around 10 times faster, right? And again, it's not just driving the time of result, but also like the ease of use, right? How quickly, easily we could make one line of code change of the model, and then ease of use of using the REST API, not necessarily just for the job to Watson Machine Learning Accelerator, but at the same time, you can keep all the data science experience in Watson Studio, right? And monitor our job, right? The status of running. At the same time, I move down a bit, where you can also monitor the metric, right, of your training, of the model training. And if you observe any accuracy or loss, they are not, either your model is not converging and they're diverging, you can actually terminate your model, go back to the previous step, retune your parameters, and kick off the train again, right? And also like scrolling down, you can see like different REST API where you can query if your training failed, right? Somehow we want to find out, go back to the training log model log, right? Model log, and see what's going on. And you can use the REST API, query the all this model training log, and debug over here. And last but not for the least, right? We have the REST API where you can query the trained model, right? From Watson Machine Learning Accelerator back to your working environment. Okay, so let me go back. I think that the training probably finished at this time. Yeah, so it's done naturally. So you see it's real time. So it's slightly different from 141 second to 138. But you see that the power of the GPUs, right? On the neural network, right, with this part just ResNet 18, we accelerate the training from 30 minutes down to 139 seconds, more than 10 times performance, right? So this, let me swap back to my slide. So now you see how data scientists, right, single data scientists accessing what's the machine learning accelerator, deep learning surface, right, achieve time to result. Now, we talk about we transition to the AI journey, to next step. Now, the clients, right, or the customer, right, they find out, well, wow, this is really cool, right? Machine learning, deep learning, helping me with GPUs, helping me to expedite time to result, and I can infuse my my AI into my application. I want to expand my team. Now that comes to the challenge, right? As I mentioned, the same model, same challenge with from when talk to client ITDs and ops data science team, they find themselves now they start to grow their data science team, and they don't have much with I would say limited ability to try to allocate and control this expensive GPU compute resource, and then end up they put themselves into silos, right? Again, this is costing inefficient, and in the next demo, is exactly what I want to show you. This is the key value of Watson Machine Learning Accelerator. How can we virtualize all of this GPU hardware, and then leveraging our capability of sharing of GPU resource and optimization of workload, so that we eliminating the resource silos, consolidating that GPU resource, and then help our clients, right? Different team of data scientists to share that virtual GPU resource pool, right? So to achieve two things, right? Drive hardware utilization, reduce total cost of ownership, at the same time, drive productivity of data scientists, and guarantee every single data scientist from different line of business to have the GPUs when they need it to do the experiment. So the technology that we apply to enable the dynamic sharing of GPUs is called elastic distributed training in Watson Machine Learning Accelerator. So this is the scenario I'm going to show you. So, but instead of 8 GPUs, I have 2 GPUs in my environment. So I'm going to show you 2 data scientists, Travis and Kelvin. They come in on board at the same time, around the same time, and they both submit the jobs, try to getting the maximum number of GPUs from the resource grid, and we can see how later on, when the job one is submit, hoarding all the 2 GPUs, when the job 2 comes in, his block, the job 2 is blocked and not going anywhere, right? But how EDT, elastic distributed training, can help, right, in dynamic fashion without any interruption of the job, to dynamically preempt one GPU from job 1 and assign to job 2, right? So let's see how it works. So I'm going to switching back to my live demo environment. So we already log into as one user, DSC user. So what I'm going to do here, I'm going back to my Cloud for Data Watson Studio UI. I'm going to add an asset. Now this time, we're not using the notebook. We're using the UI, right? The experiment, the new deep learning experiment UI, which is a click tool for submitting job to Watson Machine Learning Accelerator. So let's do the first one. We'll put down the name of the job, and then we'll put down the directed path of this data that's meant to PV the volume, and we tell the model where to grab that data, right? That we pre-upload because of this demo, and to put this data set and train this model. So next we'll define the model train definition. So again, we download the PyTorch MINS model, and there are a few lines of code change. For example, invoking the EDT API, and then in the API tells like how many GPUs, how many epochs you want to run, and then hand it over to EDT to manage the distribution of the training across multiple GPUs. So I'm not going to show this here because of the time, but I have a blog which I'll show you at the end of this after this presentation. And you can find more information. So what you're going to do, we set up all this this model along with some helper class which pull the metric from Watson Machine Learning Accelerator and display and propagate and display at Hyperparameter Watson Studio UI. So I'll drag and drop the zip file here. And over here, we select the framework we want to run and train this model. This is a PyTorch. No, this is not the right one. Sorry. And then next, we'll put down the name of the model. So I'll just, I think it's better copy and paste, so no mistake. And here, depends on how you code your model, you can pass in parameters, right, as an argument. So here, I put down number of epochs I want to run against this model. And on the right, you can see, right, we select elastic distributed training model, and we select number of GPUs, right? We want to distribute this training and accelerate this training. I'll put 2 because there are only there are 2 GPUs here. Okay, so now we create a training definition. We'll submit that the first job, right? Travis, right? And to Watson Machine Learning Accelerator. Now we're gonna log off, right? Assume second data scientist, Kelvin, coming in now. Go on to the copy for data with a given ID. Log onto his project. Pretty much ready, right? To expedite his training, right, of his PyTorch resident model, and do the same thing, right? Go on to trigger the deep learning experiment request. And now I'll go through this very quickly. It's the same submission. And this time, we're going to reuse the same existing training definition we just created. And again, right, we select PyTorch. And Kelvin also wants to take advantage of all the GPUs, right, in the grid and submit his job. Okay, so I'm going to swap to another view, right? And so we can see from system admin perspective, how can we monitor, right, all running jobs existing, running, executing in the grid at the same time, how resource being allocated to different tenant in the environment. Let me make sure that this is submit. Okay, so it is. Okay. So if you scroll down, right, on the copy for data, you see there actually right now two jobs being submitted, right? And go over, and from data science perspective, now I could actually see, right, my jobs running over here, and I will show you how to monitor the job, the metric, right, the training progress. And now I swap to Watson Machine Learning Accelerator console, and you see here the first job sending in is taking the 2 GPUs, right? And now this comes to this classic challenge, or where data science our client talking to us. How can we manage this GPUs more efficiently and be able to share across different data scientists across line of business, right? So in typical case, right, when job 1 submit, right, taking all 2 GPUs, when job 2 coming in, job 2 will be blocked, right? So the choice is whether we go back to job 1 to go to the data scientist and say, hey, you know, and negotiate, hey, can we interrupt job 1, right? And then we define the network topology, distribution topology in the model, so then we can share one-on-one GPU. Now, this is ideal for first data scientists, because imagine if the job 1 has been running for like 2 days, we're going to lose the progress of the training. So, and that will reduce the data science one Travis in this case productivity, right? But at the same time, if this job 1 can run for a long time, right, and then that means like data scientist Kelvin will be blocked and doesn't get his machine starve the GPUs to do his experimentation. Now, what we show here is exactly EDT would help. The aha moment, right? I click a refresh, bingo. This is EDT capability of preemption of GPU from job 1, right? What it does, it won't pull the GPU right away, because you previous before I hit the refresh, you see the job 2 is still running. What it does, it waits for job 1 will finish his current epoch training when we reach the synchronization boundary, and make sure that the learning, the gradient of across 2 GPUs, they sync up, and then the scheduler recognize, okay, now we hit the synchronization boundary, we finished the gradient synchronization. Now let's gracefully preempt 1 GPU from job 1 without killing it, and then we allocate that GPU to job 2, right? So, and now you have 2 happy data scientists, which they get their own resources, right, to run to do the experimentation by having their share of GPUs, right, that guaranteed by the SLA policy that defined by system admin. And you can also see here, right, elastic distributed training will kick off a job as minimum of 1 GPU. So unlike open source approach, right, if you define this training, right, would distribute across let's say 4 GPUs, the job will not start unless the resource, the 4 GPUs that resource request being guaranteed, being committed. So that's another beauty of GPUs, right? It could run with minimum of 1 GPUs, and EDT will always going back, right? So let's say if when job 1 finish, right, it will take some time actually. When this GPU return back to the resource grid, job 2, because it's asking for 2 GPUs, the scheduler will try to always go back at each epoch to the resource grid and see if there's available GPUs. At the same time, if there's no running other requests, right, needing that GPU, the scheduler would then auto scale out job 2, expedite the training from 1 to 2 GPUs. Right? And now let's go back to Cloudflare for data. Right, so I'm data scientist. This is my control plane using Watson Studio, right? Submit my job, and you see here, right, with the helper class, we put it in a zip file, and now I can monitor my training progress. And you see right here, we code, right? We want to measure the accuracy and the loss, but you could pretty much pull different parameters, right? You want to measure against your experiment or the training, and pull this information from Watson Machine Learning Accelerator and display that in Watson Studio control plane UI. Okay. So that wraps up the live demo action of what I have. Oh, by the way, for the last part, I'm sorry. So question always being asked is like, okay, how can I then, from system admin perspective, how can I manage the resource being shared, right? How can I define the resource plan for GPU resource share across different project and data scientists? So we have this concept resource plan. Of course, we have this RBAC concept. Only the admin system admin with authority can lock on and see this view. And you see here, there are different projects, right? So right here, you see so many because this is exactly each Watson Studio project, right? When you submit the request, we'll correct the resource plan, tenant not this in this resource plan, and by default, right, it's a fair share, right? So you can think of EDT. There's another key capability. Assume like you have 4 GPUs in the grid. You have 2 jobs submitted, right? 2 and 2. Now, system admin, right, can actually come and adjust the share ratio of GPUs, right? Let's say they can adjust 3 to 1. So in this case, 1 GPU will preempt from 1 job and assign to the job 2, right? That associate with this the tenant of this resource plan. So this is on the fly to satisfy business priority. Right? At the same time, you can put down the GPU quota. So by default, we'll set the next one, so it's infinite. But you can manage number of GPUs, right? Upper limit per project, per tenant that could take access from the GPU grid. So is there a question,
okay.
Travis?
Yeah, Kelvin, there was two questions. One I just answered with what you just said, right? The first question was, they want to allocate an upper limit of GPUs to a job, right? While job to allow multiple jobs. You just said, yes, you can absolutely do that.
Yep.
So anything else you want to say on that question about upper limit and setting the GPU resources?
Yeah, so this is what exactly I show here, right? So the limit, right? You could, I think there are two aspects. One is when you go back to the submission, how many GPUs the data scientist is asking for? You can put like 100, right? But it's actually controlled and managed by the resource plan defined here. But in this case, if it's -1, the schedule is always going back to the actual resource pool and see how many GPUs there and guarantee that. But not necessarily it can start with minimum of 1. I think that's the beauty of it. You won't be blocked, right? You won't be blocked because you ask for 10 GPUs. You don't get the 10 GPUs, you're stuck. No, that's not the case. You always go back. You can start your job with 1 GPUs, and you start from there. And then you don't have to worry about, right, the auto scale down. Whether there's available GPUs in the grid, the scheduler will take care of that. And that's the beauty of it. So we want to abstract that scheduling workload from data scientists. They don't have to worry about it, but they focus and spend their time instead to do the data science experimentation.
Gotcha. Hey, Kelvin, so there's a follow-on question, or a different question, actually. It says, with only 1 available GPU, is there optimization possible to allocate, say, fractional GPUs or a combination of CPU and GPUs with that use case?
We do, actually. This is a demo I'm not showing here. We have this concept of batching. So we support a slicing of a single GPU to accommodate running, for example, 2 jobs and sharing this GPU, like let's say 50-50. But it depends, right, on the application, the requirement of the GPU memory. So I think data science, they have to manage that. Otherwise, you run into out of memory situation. But it does. We support that. So the data scientists, they have to specify the memory of the GPU they request when they submit the job, and then tell the scheduler, I want, let's say, a 32 gigabyte V100. I want 60 gigabyte to train my model and accommodating my data pipeline data set. That is configurable and it's doable. This is actually a good idea. Maybe in my future demo, I'll add that use case and show client how to share single GPUs across multiple jobs. Thank you. Thank you for that question.
I think that's it for questions out in the chat.
Okay, so I'm gonna go back to my slide, and thank you, Travis, and wrap up the presentation. So one more slide, right? Overhead. So you see here in-house, right? We scale up, there's always overhead, but we have algorithm that we develop in-house, and we show that, right, with 48 GPUs across 8 hosts, we achieved 94% scaling efficiency, right? So it's very low overhead for distributing single training across with a model ResNet 52 across 48 GPUs. So I showed that already. So, and the last, right? So pointer, right? What's next? So we build lots of good resource and asset. We encourage you to, all this demo, right? That I show you, we create a corresponding show and tell video, a quick overview video. Go there and take a look, right? At the same time, now I'm very interested. I want to get hands-on. What can I do? Yes. So every single notebook I present in this session, you can find that from our guided learning path, step by step to you can execute and follow the video and the instruction we document in this learning journey to try that out yourself. Explore the capability of Watson Machine Learning Accelerator to help you to drive time to result and reduce TCO. At the same time, we have 2 blogs, right? And this is recently I just published to tell this actually the same story, right? I tell in this session how we help our clients, right, to build their enterprise AI platform at scale by leveraging the Watson Machine Learning Accelerator, managing the GPU resource, managing the GPU workload, etc. And of course, the expert Q&A, common questions that people having raising with Watson Machine Learning Accelerator. We publish this Q&A like 12 questions in this block. So that wraps up my presentation. I think we still have 10 minutes, 9 minutes for a question.